we got to shoot through a little bit of it. So, and we did end up getting some data on the 1 meter, which is nice. We got a supernova, not this one, but a superluminous supernova, and we got this galaxy here. So,
how many people were at the telescope for the first time last night? Oh, it's any telescope. First time, right?
So, you guys today, it's a busy day, right? You guys, there's a lot that we've thrown at you. You have the tools now to analyze these data. You can reduce this data. You can do image subtraction, see if you can find a new supernova, right? So we'll leave that to homework. We're not going to do that right now. Let me pull this down. So we're going to talk about spectroscopy now. And I appreciate that this is the fourth lecture you guys have had today, and it's the second day, and you're feeling it. But this is actually not so bad, because really spectroscopy, you already know all the pieces that you need to know, right? All spectroscopy is it's just photometry, just on an industrial scale. So instead of doing one band at a time, I'll do my B band and my V band and my R band. You just do all of them at the same time, right? That's really all it is. But all the techniques are really the same. There's an added fun that you don't know, which is the B band and the V band. You don't know the wavelength, so you have to figure that out. But other than that, it's just the same tools that you guys already know for doing photometry. So I'm going to talk a little bit about spectroscopy. We'll start with a little bit of motivation, and then we'll talk about how spectrographs work, just kind of broadly. And then we'll talk a little bit about how you actually go about extracting the information from a spectra and actually coming up with your extracted final spectrum. And then you'll have a module where you can actually put this to use and actually do it. So just to remind you, we've been working mostly with images so far, and images are great. They're pretty, nice to look at. They do carry some useful information. In an image, if you take an image and you see something in it, you know it's there. That's important. You can see its relative position. Is it somewhere, how far is it from some other object? Does it move over time? It could be an asteroid. That's an interesting thing to note. If it doesn't move over time, maybe it's very far away. So you learn something from that. The brightness is another important thing you get from photometry. How bright is it relative to other objects? Does it change in time? Does it get brighter? Right? So it could be a supernova, and it can get very bright over time, then fade away. You can tell that through photometry. You get some information about angular size too. I mean, typically, if you're looking at a star or something, you just get a limit. It's smaller than a pixel. But if you're looking at a galaxy, you can see it's extended, and it'll tell you something about its physical size. An important thing that you can also get from just photometry is color. And you get this if you take two exposures in different bands. Right? You need two different bands. And then you can compare ratio of counts that you get in one band compared to the other. So you take use a red filter, and you'll get some number of counts, and you'll do a blue filter and get some number of counts. And you look at the ratio of that. That ratio is your color. And that's telling you something physical about the object, which is important. And this is really the key thing for this talk. It's color. There's information that you get in different bands, right? So if I look at a blue band or a red band, infrared band, you get slightly different information. So really what you want to do is you want to get all that information. And that's what you're getting with spectroscopy. So let's just take a look at an actual image. If I can. So here's an image. This is an image taken by a Sloan Digital Sky Survey. I just downloaded. You can look at this, and again, you can say this is something. What is this right here? Well, it's not the whirlpool. It's a galaxy. It's actually some nondescript galaxy. I don't know which one it is. But there's a galaxy here, and this is probably a star. And there's a little thing here. Maybe that's part of this galaxy. Maybe it's another galaxy. But we don't know. We don't really know what this is. This could be a star. Maybe it's a supernova in this galaxy. I don't know. From this image, you can't tell that. If you just show me this image, I go, well, that's cool. But that's all really you can say about it. You can add color information. You can start kind of guessing a little bit. Maybe you can get a guess that these two galaxies have similar colors. Maybe they're similar redshifts. Maybe not. We don't know. But what you really want to do is you want to figure out more about this. What is this? We're scientists, and we want to know, what is this? What is it made of? How does it work? What is it doing? And to do that, we need more information than we can get from just a single picture here. So that's why we're turning to spectroscopy. So this is now a spectrum of that same galaxy. This is also from the Sloan Digital Sky Survey, and all it is, let me actually go back. Whoa, not that far. Not that far. There we go. What they did is they just basically are looking at the center of this galaxy here, and they're summing up all the light here and taking a spectrum of it, and we can see in a little more detail what we have here. So this is what the core of that galaxy looks like as a spectrum. This is wavelength here. This is in angstroms, 4,000. This is your blue lights over here. This is red light over here. This is getting into near infrared. And this is basically relative intensity as a function of wavelength in each one of these bins, right? And you can see that you have this continuum here. So there's, some background of light. And on top of that, there's these spikes here. And these are real, right? This one's not real. This one's real. This one's real. And this is telling you something about what this object is. These, of course, are emission lines from that galaxy, right? And they're conveying information. They're saying there is oxygen in that galaxy. There is hydrogen in that galaxy. There is sulfur, right? We know the content of this. Now, we can't go there. We can't actually taste this galaxy or smell it or, do anything physical with it. But I can tell you that galaxy far, far away has oxygen and helium and hydrogen in it. We can look at this redshift here, and I can say, well, in the laboratory, this is supposed to be over here. It's been shifted over. That means it's moving away from us. It's been Doppler shifted, right? So again, when I'm not there, I can't measure its speed with a radar gun or anything. Well, I kind of can, but using this, a fancy radar gun we're using. But I can tell you information about it just by getting this spectrum here. We can also look at the ratios of these lines and compare, this oxygen line to these oxygen lines and say, well, that's actually a pretty hot galaxy to get these emission lines, or the gas that's emitting here, maybe not the whole galaxy, but the gas responsible for this, we can assign a temperature to that. So I can give you the temperature, I can tell you its recession velocity, how fast it's moving away from us, and physically what it's made of, given this spectrum. All right. A lot of information contained in spectra. And that's why you want to get spectra. Just for comparison here, when you're doing photometry, here's what you're doing. You're getting all those same photons. Right? You start with this blue spectrum. You get all the same photons. But what you do is you put in a filter. It looks something like this. This is a G-band filter. Right? What you say is you just take all the light that comes just in this band. Right? So you're doing a convolution. You're taking this filter function here, and for every wavelength, you're multiplying this value by this value, and this value by this value, and taking all those values, those multiplied products, and you add them all together, and you get one number, right? So for photometry, G-band, you get one number, which is 10,000, and that doesn't tell you anything about these lines, these individual lines. It's too broad of a filter for that to happen. So this is why we want to go to higher and higher resolution. The higher resolution you go, which means the narrower these bands are, the more we can resolve individual features and we can start learning what this object is physically. All right. So just to reiterate, here's the kind of the key information you can get from a spectrum. You can get temperature, composition, line of sight. And you might say, well, if you give me enough photometry, I can get temperature, right? You give me multiple bands and I can fit a black body to it and I can kind of get a gauge of the temperature. But what you're doing there is actually spectroscopy, right? Once you start using multiple bands, that's spectroscopy. It's just low resolution spectroscopy, right? You give me higher resolution, I can tell you more about it. So resolution, by the way, is just defined as whatever your bandpass is and the central wavelength. Just divide the central wavelength by the bandpass. And so, for example, when you're doing photometry, just to put some numbers on this. So if you have a band like this band here, so this is the R band in Sloan, it's around 6,000 angstroms, let's say, and it's about 1,000 angstroms wide. So the resolution of this band is 6. 6,000 divided by 1,000, it's a resolution of 6. The spectrum here, right, at this wavelength here, so at a wavelength of 6,000, the bin here is, I forget for Sloan, it's something like, well, let's just say it's an angstrom. Let me say 6 angstroms. It's probably close to 6 angstroms. So the resolution for this spectrum is 1,000. And that's a typical low resolution spectrum. So you're getting, roughly 1,000 times more information in the spectrum than you are in the broadband photometry. All right. So you guys can do math. A picture is worth 1,000 words, right? So the moral today is that a spectrum is worth 1,000,000 words, right? That's how the math works out. We all want spectra. Spectra are great, but they come at a cost. And that cost is you're taking all those photons you're getting, these precious few photons from this galaxy far, far away, and you're spreading them out on your detector, all right? And you're just measuring just a few at a time in these little tiny bins. And the smaller and smaller you make those bins, the fewer and fewer photons you get in those bins, and the more noise you're going to get and the harder it gets. So spectroscopy, we say, is aperture hungry. You need a big telescope if you want to get a spectrum of a faint object. So that's why at Mount Laguna we have a 1-meter telescope. We do have a spectrograph there. There's not a lot of science that we're doing with that spectrograph because of aperture effects and because that it's not the most sensitive spectrograph we have. But it's hard to do things in small aperture telescopes. All right. All right, so you guys got a good sense of why we want to do spectroscopy. All right, now let's talk about how we do spectroscopy. We got to disperse the light. Light's coming to us, it's all together. We want to break it up into different wavelengths. Ideally, in the future, we'll have nice detectors where a photon comes in and we'll measure its position and its wavelength and everything just in one shot. Not quite there yet, so what we're actually doing is we're dispersing the light and we're putting it on the same detectors you guys are already studying, CCDs. You have the light fall on a CCD, and if it's dispersed into a rainbow, then at different positions on your CCD, you're getting different wavelengths. All right, so that's the key thing here. There's two basic ways that you can disperse light. You can put a prism down, right? And white light comes in. You use Snell's law here, and you figure out that, well, as a function of wavelength, I'm going to get some dispersion on the way out here. So you get white light in, you get rainbows out, right? We use this sometimes in astronomy, but more popular is using this effect, which is a diffraction grating. So you have this material here that has a bunch of grooves in it, which you can kind of see in this drawing here. There's a bunch of grooves going across here, and white light comes in, and then you get interference. And so some of the white light goes straight through, but then you get interference, which causes, as a function of wavelength, intensity peaks, right? So and you'll get a positive order, a negative order, and you get second order, minus second order, and you'll get your 0th order. So I'm going to tell you a little bit about this device and make sure you guys know how that works. All right. So the principle is based on something that you guys have probably done in high school or as an undergrad. You guys know that the double slit experiment? Everybody did the double slit experiment? All right, so you take, the slit's not this big, by the way. Usually the slits are very, very tiny, and you shine a laser on the slit, and the light goes through. And you know that if you look at some angle, right, that light going through this hole, this slit, and light going through this slit are going to have a path length difference. And this path length difference is going to depend on this angle here. And if it works out, the path length difference is an integer number, m, of the wavelength of the light, right? That means that you have light coming in through here, and you light coming in through here. And this one does one extra full cycle here, and then they're both in phase, and then they go and they add constructively, right? Remember all this? Right, perfect. So if you have some angle at some wavelength, you'll get an intensity peak. If this is the half integer, then this one's doing this, and this one's doing this, and they cancel out, right? And you don't get anything. All right, so this is the basic principle that you need for spectroscopy. You guys all did this experiment. When you did it, you guys used lasers probably, right? You shot a laser. What color was the laser? Mostly you were red, some green. Did anybody do both red and green? You never do red and green. Well, it's interesting if you try both. Let's see what happens if you do both. Let's think about this. So I wrote just a fake little code here to kind of simulate this thing. So we're going to make fringes like you do. We're going to have some detector at some distance. What we're going to do is we're going to have a spacing between our fake slits, and there's going to be different path lengths to our detector for each one of these slits. And we're going to compare that path length, And then we're going to see, do we get constructive or deconstructive interference, all right? So we can just run this here, and so I'm just plotting my detector coordinates here, and I'm plotting the intensity here. So this means constructive interference, this means destructive interference. And then as a function of position on my detector, you see it's going up and down. So we get peaks and troughs. And I'm ignoring some other important physics right now just to make it simple. You know that this decays over as you move away from the center, but I'm just ignoring that for now. So this is for some given fake wavelength. I just 0.1 in whatever units you want to be. And I'm just drawing that with blue. Let's do it at a different wavelength. This is what's important for spectroscopy. Let's make this, instead of 1.1, make it a bit longer wavelength. All right, and we'll plot it with a redder color so we know it's longer. And here's what you get. Right? This is how spectroscopy works. The 0th order, okay, things align. But as you move away from that, you'll notice the peaks get farther and farther apart. Okay? They don't line up perfectly. And this just goes back to that equation that we were looking at before, which depends on wavelength here. This angle is dependent on the wavelength. So longer wavelength light is going to be dispersed more. Right? The peaks, I should say, are going to be farther apart. That's what we're learning here. All right? You guys seen this before? I wish they'd do two-color lasers. Make life a little bit easier when you get to this level. But I guess it's enough at that level. One laser is probably enough to start. All right. So that's with light through a slit. Let's move towards a grating. So this is now not just two little slits. This is lots and lots and lots and lots and lots of slits. This is hundreds of slits per millimeter on here. And if you do that, you end up with, you shine white light through here, and you get this effect that we're just looking at here. Actually, let me show you a real one of these. So this is a grating here. Right? You guys get to play with these sometimes. You get to look at things, and you can see little rainbows if you hold them up to your eye. If you shine a green laser through it, I'll just do it on the board here. All right, you see all those different orders? So it's just a laser. It looks clear, but there's lots and lots of grooves in here. There's 500 lines per millimeter on this. And if you shine that, you get all those different orders. Right? I'm sorry if I'm getting you. It's hard to do this experiment. And if I do a red laser, you can kind of see it. The red's a little, whoa, it's a little weaker. It's not working, of course. So I have my backup. Let's see if this works. That's pretty weak, too. You can kind of see it, right? You get those orders here. And the key thing is, if you line up the 0th order, you can see the red is farther spaced than the green, right? You guys see that? So there's spectroscopy. That's how we can do things with these. All right, so that works in transmission. These are transmission gratings, light's coming through and being dispersed. You can also do this in reflection. All right, same principle applies. You just need a regular pattern, right? And you need it to be, as long as you have a regular pattern, you're going to get this effect, all right? So we can illustrate this. There's different ways to illustrate it. Usually this is where you pull out, historically at least, we'd get like a CD, and we'd show it to the class. And you know CDs? You guys know CDs? Maybe you don't, right? Maybe DVDs, Blu-rays. You probably still got Blu-rays at least. But you guys get your MP3s and 4s and all that. You don't know maybe that CDs have grooves on them, and you get the same effect on that. So you can show up a CD and do that. What I found actually works pretty good is as your phone, right? If you turn off the display, you get a nice black screen, right? There's a regular pattern on here. You got pixels on here, right? So does this act as a diffraction grating? You bet it does. Right? All you need to do is find a point source of light, which I have, but you guys probably don't. So here's what I'll do. I'll give you a point source. If you have your phone, you want to try this, you got to turn the screen off, and you got to look at me like this, right? So look at the reflection in here, and I'm my light, and if you look at this light, and you have your phone behind you, if it's bright, it's a little bright in here. Can you see the rainbows? You got to be able to angle it. Is anybody able to do it? It's a little bright in here. You can do it. Front row can do it. Does it work in the back row? Yeah. So it looks like rainbows, right? Yeah. All right. One of the rare occasions when the professor says, everyone get your phones out. Doesn't happen often. All right, so that's a transmission grating. I have another grating. This is an actual one that we used to use at the observatory. So you guys saw that spectrograph? It has gratings like this. This is one that we use in the telescope. This one got damaged, so it is now a lab demo. But this is 831 lines per millimeter, and I will try not to blind you guys and make rainbows over there. So you can see there's the first order. See right there. There's the first order. I'm sorry, that's the 0th order. I'm saying it wrong. 0th order. There's the first, second. I don't really see the third. There can be more, but the way that these gratings are designed, you can see there's actually a limit to how many orders you're going to get, which is good because you don't want all the light to go into one order, as you'll see. You don't want a million orders. You want most of the light to go in one order because that's the one you're going to measure. There's also, you can't really see there, but there's also a -1 you can see, very faint. So 0, -1. Okay? All right. All right. So we're going to use this now. So we know now how we can make rainbows. Now we want to know how we can actually get some data out of this. So how am I doing? I got a few minutes. Okay. We can do this. All right. So let's actually do some spectroscopy now. But we're going to start with just a fake little test case here just to illustrate the point. So we start off with imaging. Right? You got a telescope that takes images. You have a detector, and you can take pictures of the sky. This is actually just your focal plane, for example. And you maybe have some stars in here. So what you want to do is you take your telescope and you put a dispersive element in it. And you get rainbows, right? Very cartoony, I know, but it'll work out. I'm ignoring some things here. I'm only showing one order. I'm showing the 0th order and the first order, so 2 technically. I'm not showing higher orders or negative orders. But you'll get the idea. So you can disperse light from these stars. Okay? Now, you might notice there's an issue with this. The light gets spread out over many, many pixels. And that means if you have 2 objects which are aligned along your perpendicular to your grooves on your dispersive element, they can overlap. And this causes problems. You get 2 objects on the same pixel at different wavelengths. That's really hard to deal with. So what we often do is we'll put in a mask, right? Right? And what a mask does is you just block out all those other objects. You only let light in from some part of the detector. Typically it's a slit, but do not confuse this slit with the slit you guys did in high school, right? It's not your double slit experiment anymore. This is just a mask. We call it a slit because it happens to be a slit, but it has no dispersive properties. It's just to block out other light. And so now you just have one object. This is the one we care about, and we're dispersing the light over here. And of course, the last thing you have to do is you have to put your detector on that light. And you saw before, the light gets spread out. We'll show you a couple things. Let me put what's it going to do? Put in the detector. There you go. So you have some area where you have your detector. And notice the detector is smaller than this trace here, right? You might say, well, why is that? Well, it's because these are expensive, people. You can't make one that's big enough, right? Did you see how big that beam was? Look at this again. Where is it? Where is it? There it is. Right? That's big. You don't have silicon that big, so often you'll just get a little piece of this. Right? And keep that in mind. So one thing you can do, though, is you can move the grating. So if I tilt it, I can change where I put it. So maybe that piece of paper there, maybe that's my detector. Right? I can move this, and I can change what wavelength I have across there. That's one of the tricks you can do with spectroscopy. There's other ways to get more light, but this is kind of the simplest way. All right. You following along? All right. Let's keep going. So let's get to a real instrument. This is a schematic of a real instrument. This is Keck LRES. This is actually the GUI that you use to operate it, but it has a nice schematic of how it works. Light is coming from the telescope into the instrument here. It's got a lens here. It's got a collimator here. Light goes to a grating like the one I showed you, and it goes into a camera, and you take a picture of the rainbow. Right? That's spectroscopy. This is a fancy spectrograph. It has a double beam, which means there's a pick-off here, which is a dichroic mirror. This reflects blue light and transmits red light, so you get two channels. The blue light goes into this camera, red light goes in this camera. And they also have another element here. This is a grism, and as the name implies, this is somewhere between a prism and a grating. Right? It's actually got a prism shape, and it's got little gratings, little notches on it like a grating. And so light goes through here and is dispersed here into this camera. Yeah?
What do you do with the 0th order light?
What do you do with the 0th order light? The first technique you can do is if that's my detector over there, that piece of paper, right? So there's my 0th order light on the detector. I'll just move it off my detector. Yeah. That's one thing you can do. You can also design your optics to minimize that 0th order. As you can see, it's not very bright. Right? That 0th order in this particular grism is not bright. The first order here is brighter.
So
right?
What do you do to minimize how much light goes into?
It's how you have the grooves set up on here. So, if you, it has a little bit to do about the tilt and what the gratings is. So if I go back, if you just study this, I'm not going to go into detail on this, but if you study this and you think about different tilts, light that's going to get reflected, say this way, is going to hit this thing. It can't do that, so it won't, and so you won't get that order visible. All the light will go into a different order. So little tricks like that will get you just one order. Yeah. Other tricks. There's one other trick, which for the
really grazing instruments would give you no 0th order.
I don't know about no 0th order. It's tough to get no 0th order with this kind of setup. I have to think about a more advanced way to do it. Yeah. All right. Let me go back. One more question, yes?
Do you use that 0th order to do simultaneous imaging?
You can, although it tends to be distorted, right? This is not designed to make a perfect reflection. It's designed to do something else. So you get kind of a distorted image, but it is possible. And this is especially true with grism spectroscopy. If you're taking grism spectroscopy, usually you get a nice, pretty bright, actually, first order image, a 0th order image, and you'll get other orders there. You can do something with that if you wanted to. Usually it's just, for most applications, it ends up being annoying. All right, here's what we're doing now. Did I skip something? Okay, so we have this system lined up. Let's start with a cartoon spectrum just to walk you through what we're going to do to extract this spectrum. So this is, I just wrote a little function here to make a fake spectrum for you. And all it's showing here, we have wavelength across this coordinate here, and we have spatial coordinate along here, right? So you think about that rainbow we saw on there. You had, a vertical band had one color, right? You had red in one vertical band, blue was over here, etc. So same thing is going here. This is one color, this is one color, and as you're going, you're changing wavelength. Here are spatial coordinates. So as you're moving across here, you're looking at different things on the sky, usually. So right here, we have an object located here on the sky, and this is its spectrum. Right? So as a function of wavelength, right, at one position, it changes as a function of wavelength, we get the spectrum there. On top of this, if you go to any spatial coordinates, like this one here, any wavelength coordinate, and you change the spatial coordinate, you'll see that there's also some extended emission at certain wavelengths. Right? So what this is saying is that these lines don't depend on your spatial coordinate. Right? This is your background. These are sky lines, for example. Right? This is light that you don't care about, but it's going to be everywhere. Right? So just like when you do photometry and there's background light, spectroscopy, you got background light too, and you have to deal with that. So how do we deal with that? Let's skip that. The way we do this is pretty straightforward. It's just like I said, just like photometry. You're going to, I'll just show this other thing. This might be easier. If you want to know how bright this object is at this particular wavelength, what you do is you put down an aperture. right? It's going to be a one-dimensional aperture now. And from here to here, you're just going to count how many photons you got, right? This is going to include background light. So you also need a background aperture. And you measure how many counts you get in your background. You subtract it from this, and then you've got your counts from the object alone in this particular wavelength band. And then you just do that, in this case, 500 times, right? And you're done. So let's actually do that on this test case here. Oops, let me go over here. So I've got, that's what it's going to look like. We've got this spectrum. We have this image that I made. This is my fake image that has all the information we need in it. And what I'm going to do is I can just take a sum along each one of those columns. I'll use axis. This is a very handy command if you don't know it. Axis equals 0. This is all NumPy. I'm just using NumPy here. Axis equals 0, and I'll get a spectrum. And this is what it looks like. So this is, I'm just integrating, each one of those columns, summing up, and plotting it as a function of my wavelength coordinate, and we'll see the relative flux density for this object. Now we want to get rid of these emission lines. We know our original target didn't have that. So you do something analogous to photometry, and you just extract, instead of the entire image, you can extract just the part of the image that has the target, right? So maybe it's in rows 80 to 120, right? And we'll take all the columns. And, sorry, yes, that's right. And then we will extract the sky background, which is just the image going from some other part. This is our sky aperture, so maybe 20 to 60, just to make things easy, right? And so if we take the part where we have our target, subtract off some sky background, this is what we get. Right? This is our target spectrum with the skyline magically gone. All right. So that's what we want to do. And after we've done this, we still have just wavelength coordinate here. We have to figure out what each one of these wavelengths are. And that's where that sky background actually can help us, because the sky background has all those emission lines. And if we know the wavelengths of these emission lines, then we can actually calibrate this. So if I know that this is, say, oxygen 5577, then I know this coordinate is 5577. And if I know this coordinate, then I can work out a solution, and I can figure out what the wavelengths are for everything, and I can apply that to my science spectrum, and I've got a full spectrum. All right. All right. So that's what you guys are going to do. Let me show you the data you're going to be working with. So now this has all been fake data just for fun. Now we're going to look at some real data. I'll skip that. Let's look at real data. So this is data that you can use to figure out your wavelength solution. So this is just an exposure where we've injected a lamp that has emission lines at known wavelengths. Right? This is an arc lamp. So we can identify each one of these lines here and then use that to calibrate our wavelength system. Or you can alternatively, you can use skylines if you have enough of them. Another thing, we got to do flat fielding, right? So just like in photometry, you got to do flat fielding, and if you want to do a flat field, you have a G-band exposure, you need a flat field and a G-band exposure. So all we need to do is take one flat, and then each one of these columns again, this is just telling us our wavelength, how bright the object is at a particular wavelength, and we'll just use that particular column for our data, just the average on that, just like you do on flat fielding, on photometry. This is what a standard star looks like. So at some point you might want to calibrate your observations. You might want to say at this particular wavelength, relative to some other object, how bright is our target? So you observe a star where someone has already gone through all the hard work of calibrating at each one of these bins how bright the target is. And then you say, well, I got 50 counts here. Well, that's more than 50. Maybe 10,000 counts here. And I know this is the flux. So here's my conversion factor at this particular wavelength to go from my counts into flux units. And then the most important thing, here's your science spectrum. So this is, again, a real spectrum. This is taken by, actually taken by Dan Perley right over there. This is real data from Keck of a real target. This is your target right down here. This is just a random object that happens to be in the slit. You can extract that one too if you want. But this, you'll notice there's a continuum here, and then there's some emission lines on top of it that are localized towards this object. Right? So this is a galaxy. There's a galaxy, and that's the starlight, is the continuum, and these are the nebular features here, those lines that you see. And you can use those lines to figure out the redshift of this object. You can also see its chemical content of the gas, but the main target for your notebook is going to be to figure out what's the redshift of this galaxy. Okay? All right, so there's a lot to this, and you'll see it very shortly if you haven't looked at the notebook yet. There's a lot to do in this notebook. You may not get through all of it, and that's fine. The approach of the notebook is not, here's something you guys can do in 10 minutes, right, or an hour. It's actually, here's how you reduce spectra, and it's very instructive on all the processes you're going to do. So if you follow every step in that notebook, you'll actually have a publication quality spectrum, right? And you can apply this to other data sets. I'm just showing you the general technique. So you may not get all the way through, but hopefully you might be able to get a redshift. That might be pushing it. And there's some additional steps to actually fully calibrate the spectrum and publish it. So I just wanted you, just a heads up on that. It might be tough going through, but hopefully this will be something that you'll have as a reference and you can use it practically in the future. So that's my presentation. Was there any questions before we move into the notebook? All right. Okay.